You can proceed.
Okay, good afternoon. So, myself Rajesh Ilakan. So, I'm going to introduce the next speaker. So, I'm going to introduce Dr. Xavier Crispin from Linköping University. Dr. Xavier Crispin graduated in chemistry in 2000 at the University of Mons, Belgium. He then joined Linköping University as a postdoctoral fellow. Currently, he is working as a professor in the Organic Electronics Laboratory, one of the leading labs across the world. So, Dr. Xavier Crispin is an expert in different spectroscopy techniques to characterize molecular order, electronic structure, and semiconducting polymers molecule, as well as studying the energetic interface between these materials and electrodes. Dr. Xavier Crispin is the recipient of 2 prestigious awards. The first one was in 2001. He just received Tage Erlander Prize from the Swedish Royal Academy of Science. In 2016, he received another prestigious prize from the Royal Academy of Science. So he received Goran Gustafsson Prize in 2016. Currently, he is working on conducting polymers as energy material in supercapacitor, thermoelectric, and fuel cell. So I would like to request Dr. Xavier Crispin to deliver his talk. Dr. Xavier?
Yes, thank you.
Yeah, you can just. Thank you.
Okay, let me see where. Now I can share screen.
So on the bottom, you can see the green color share screen.
Yes. Do you see my screen now?
Yes, yes.
Yes, yeah, we are seeing it.
You can switch it to presentation.
It works?
Yeah.
Yes.
Yes.
Yeah.
So, yeah, I don't know. Good morning or good evening for everybody. I don't know when it's the time for you, but it's a pleasure to be here among you in these strange times, and I really appreciate the initiative of this conference. So thank you for the organizer for this conference. So I'm going to talk about a little bit of my hobby, which is thermoelectric properties of polymer in general, and how to apply that for sensors, basically. So come back to a little bit of basic of thermoelectric, and we are going to look at mostly one phenomena, which is called the Seebeck effect. And here I illustrate this Seebeck effect with a metal piece, where basically you have a conductor, and inside the metal you have 3 electrons. And those electrons, this material, we will submit that to a temperature gradient. So there will be a hot side. I don't know if you see my pointer. No. There will be a hot side and a cold side here. And what is happening is that the mean free path of the hot electron is longer than the cold electron. And as a result, it is like if the electron tends to migrate towards the cold side, basically. So you look here, you basically have electrons moving those small dots in towards the cold side. And of course, the nuclei that are positively charged are immobile. So this results then in a temperature, in a voltage difference, where you have an excess of negative charge on the cold side and an excess of positive charge on the hot side. So now the difference between the voltage difference that you obtain between cold and hot side and the temperature difference you apply between the cold and hot side is called the Seebeck coefficient of the materials. So basically we are talking about the thermodiffusion of electronic charge carriers in that case in the material. Now, the phenomena of thermodiffusion is quite general. It applies to electrons, to ions, to molecules, to particles. So, for instance, if you have a very hot wire, as so hot that it can be almost reddish, you let pass a current into that, and then you blow smoke of a cigarette, and you have a look close to the wire that is hot, and you will see that there is almost no smoke particle there. because they are moving away towards the cold side. So these thermodiffusion phenomena are quite general, and here we are going to focus on two particles, that is the electrons, electronic charge carriers, as well as the ions. And because those charge carriers have a charge, then the gradient of concentration that you obtain by thermodiffusion will generate an electric potential between cold and hot side for ions and for electrons too. So the type of material that we are going to look at, these are polymeric. And polymer are nice because they have different type of properties, such as solution processibility, then printability, but also to some extent flexibility. And you can have then new shapes. And we are going to talk about new shapes with polymers. We are going to talk about, for instance, gels, but also we are going to talk about aerogels, which has very porous structure. So first we go through the general behavior of what we call conducting polymers and their thermoelectric properties. Here I call conducting polymer in a very broad sense, that is to say they conduct charge carriers, and it can be either ionic or electronic. All right. So when you speak about ions, then you will speak about electrolyte, actually. When you speak about electrons, you will speak about conjugated polymers, typically. So if you look at this graph, it shows basically the Seebeck coefficient of the different type of materials versus the conductivity of those materials. And we know that the conductivity is intrinsically also related to the charge carrier density. So for instance, if you look at metals, they have a huge charge carrier density, but they typically have a very, very tiny Seebeck coefficient of a few microvolt per Kelvin. On the contrary, if you have insulators with really little charge carriers, they typically have a large Seebeck coefficient, but they don't conduct anything, so it's not great. But looking at ions is also interesting, because these materials are not conducting the electrons, but they conduct ions, and that also lead them to have a Seebeck coefficient, which is actually quite high, very high. It's a very high value for the Seebeck coefficient. We reach nowadays in polymer electrolyte something like 20 millivolts per Kelvin, while metals have microvolts per Kelvin, so much larger number. Okay, so the question is, what are we going to do? What can we do for sensing application with polymers and looking at the their thermoelectric properties using both electrons and ions, and eventually both in the same time? So I'm going to show the three kind of polymers just to illustrate. This one on the top left is a polystyrene sulfonate. You see that the polymer chain, the skeleton of the polymer chain is only composed of single bond. So this one is not conducting electrons, but you see they have sulfonate groups here, and they promote the proton conductivity. So this one is a polymer that conducts the protons, the ions. The one on the bottom here is a derivative of polythiophane, and what you can look at is that there is an alternation of single double bond in the backbone of the polymer chain. This makes this polymer a conjugated polymer, which in that case is oxidated. That is to say, it carries also positive charge, electronic positive charge on the chain, which is balanced by counterions that are here symbolized by the X minus, in order to have a neutral material. So it's a polymer, but it's kind of a salt also in the same time, and it conducts electricity. So this one is actually a good conductor for holes, that is to say electronic charge carriers. Now it's possible also to combine those materials. So for instance, instead of using those X- that are small anions, you can actually use these sulfonate groups from the other polymer. And then you can merge them together in a blend or composite of polymer, which is in that case this P.PSS. Then you end up with a material that is quite interesting because it conducts in the same time the protons or cations, as well as electronic charge carriers in the form of holes mostly. So you have done three types of polymer: the ionic conductors, the electronic conductors, and then the mixed conductors conducting both ions and electrons. So we can look a little bit what is happening to them when we expose to humidity. When you expose to humidity, actually not much is happening for the electronic conductor. For instance, the top one, P.Tosylate, there's not much happening. Now for the ionic conductor, the PSS there, we see that when you increase the humidity, basically the ionic conductivity increased by almost 3 orders of magnitude. So it's a drastic effect when you promote ionic conductivity when you have humidity around, of course. So because the mobility of those ions is just boosted. All right. Now, if you look at the P.PSS, which is the mixed conductor, actually at a low humidity level, there is still mostly the electronic carrier that is dominating. But when you increase the humidity, what is happening is that there's a decrease and then there is an increase of conductivity, meaning that there is the ionic conductivity start to have also an impact in those materials. Also, the presence of iron and water is changing the potential landscape of the electronic charge carriers in that material too. So it can be quite complex. But you see that there is also a response to humidity when the ionic carriers kicks in. This is even more visible when you look at the evolution of the thermovoltage, that is to say, the Seebeck voltage. So in those experiments here, in the bottom, you see this is what you apply as temperature gradient to the material. All right, so you see a small temperature gradient here. So for instance, if you apply -1 degree, for the pure for the electronic conductor, these whole conductors, what you see is a direct small increase of potential here, like something like 8 microvolt. All right. Now, if you look at an ionic conductor, the PSS-Na is not conducting the electron, just the ions. Then what you see is indeed there is also an increase of potential, open circuit voltage when you apply the temperature gradient, but that one extends to huge values, close to 4 millivolt. So it's a much larger voltage that you promote by the same temperature gradient, because these are ions. Now, when you look at the mixed conductor conducting both ions and electrons, then you have a completely different behavior. There you have actually a peak. You see there is an increase of potential and then it decreases again. And then if we look a little bit closer to that, we can zoom on that one and we can vary the humidity. So what we discover is that if you look at the open circuit voltage and you apply the temperature gradient, so at more or less 100 seconds here, you apply the temperature gradient. And then you see that the potential is increased. For a very dry sample, the ions are not mobile. So what is happening is that you have a small increase of potential here, and you have actually the electronic Seebeck coefficient that you obtain. Now, when the sample gets more and more humid, you see that these peaks is growing here because the ion kicks in. So you have the ions that are start to move basically, and then there are there is a reorganization of both ions and electrons in the materials that makes this drop here. And eventually, there is still a potential difference developed after some times, and this is corresponding exactly to the electronic contribution of the Seebeck voltage. So basically, you can, in this kind of mixed conduction, you have a signal from the ion here as a peak, and the signal from the electron is as a plateau here at long time. So this is an interesting feature, because what you have is a material where actually, if you know the Seebeck coefficient, you would just measure the voltage you obtain, and then you can know the temperature gradient. In the same time, if you measure the peak here, you can know the humidity. So you can both read the humidity level at the peak value and the temperature gradient at the plateau value. So this is an interesting experience and materials where you can access actually two parameters, the temperature and the humidity, with a single material. Then we are thinking to make, okay, let's make more intelligent multifunctional materials, so that with only one material, we try to basically know as much parameter as possible, to sense as much parameter as possible. So we are going to discuss about measuring pressure, temperature, and humidity. Is it possible to measure those in one material? Yes, most of the material do have a response to humidity, temperature, and pressure. There is nothing fancy about that. But is it possible to read temperature, pressure, and humidity in an independent fashion, so that there is not any cross-talking between the different parameters? Most of them, if you apply, for instance, a pressure and temperature and humidity, you will read something, but you don't know what is the reason why it is. Is it due to the pressure, to the temperature, or the humidity? You cannot distinguish them because there is cross-talking. But here, what we try to do is to uncouple the input parameter. So we try to make intelligent multifunctional material that with one material you can access different physical parameter, temperature, pressure, and humidity, without that the material has crosstalk between those different features. So we'll try to demonstrate that. So the first things we do is we are going to talk about the dual sensor using temperature and pressure. So for that, we use an aerogel. That's a little bit the beauty of polymers, is that you can create kind of different shape. So here we make an aerogel of PEDOT-PSS. We mix that with nanofiber of cellulose, and we cross-link that with a silane agent to make it robust, and also elastomeric to some extent. So you see this, you obtain this kind of porous structure. Here you see the SEM image. This is an aerogel, then it's very porous. And the feature of it that we succeed to have is actually that it is to some extent elastic. So when you press with your finger on this kind of material here, after they recover their shape. If you try to do that with just conducting polymer, it just breaks apart. If you do that with cellulose, is not going to come back very much. So there is a combination of material that is of interest here. And those materials, because they do include PEDOT-PSS, they are actually conducting the electricity too. So we have an aerogel of conducting polymer elastase that is conducting electricity. Then what we do with that is that we try to develop this dual parameter sensor. The concept is the following. If you have a material that you squeeze between two electrodes, and you are going just to measure the IV curve, the current versus voltage. That material has a certain resistance, which is basically related to the slope of this IV curve. Now, if you press on the material, then you change the resistance of the material, you decrease the resistance of the material, and then the slope of the IV curve is changing. So the slope of the IV curve here is connected to the pressure you apply. Now, looking at temperature, if you apply a temperature gradient between the top and bottom electrode, then what is happening is that you are going to shift the IV curve by a potential, which is the Seebeck potential, the thermoelectric potential. So a temperature gradient applied will be seen as a shift in the curve here. So when you then, if you succeed to make a material that is independent, where those two parameters can be read independently without crosstalking, then you get an interesting material. So the goal is to succeed to have such a material, and such that when you apply a pressure and in the same time a temperature gradient, you can see that this curve will be shifted by a certain value, and you can access temperature, and the slope of it is a certain value, and this is connected to the pressure, so that you can read both in the same time. So this is the goal. Is it possible to do? So this is what we succeed to do, but at the beginning we did not succeed. So the material, the aerogel that we form, actually had this kind of response. You see here, this is the IV curve at different temperature gradient. And what you see is that the slope is changing while we are not applying any pressure here. We are just not applying any pressure. So normally the slope should not change, but it does change. And the reason of it is that because the resistance is a temperature dependence. So the resistance here of that material changes with the temperature. And because of that, we have a change of slope of the IV curve when we apply different temperature gradient. So that is a little bit annoying, because we would like to have something that is not like this. We would like to have only the slope change due to pressure, but here it's not any due to pressure. It's due to the intrinsic transport property of the conducting polymer. So what we have done is that we actually change the organization of the polymer by using a treatment of a vapor of DMSO. And by doing that, you actually change the morphology of the polymer, and you can have a very highly conducting polymer. So the conductivity increased by 3 orders of magnitude. And what we end up is in a material that is almost metallic. So that is to say, you're at the crossing between insulating to metallic transition, where actually the resistance is not depending on the temperature. You see, it is just independent of temperature. And then in that case, we get a very nice parallel curve here, where you see we don't apply any pressure, but we just apply a difference of temperature, and we get very nice parallel line. So this one will be then an ideal material, because now when you apply a pressure, it will be seen as a change of slope only. And indeed, here it's what you get. These are different time, different pressure. These are different slope, and each temperature gradient is a group of curve. Basically, here is a shift. So hereby, then, if you have characterized your device, whatever pressure you apply and temperature gradient you apply, you have calibrated that before, and then you can then get the extraction of the pressure and temperature gradient applied. So this is the concept of a dual parameter sensor. So we go further, and I told you these materials also are sensitive to humidity because the ions start to move. So now we have used that also in that concept. So let me go through that. So basically, it's the same kind of aerogel, but we are now using also humidity as a parameter. So as we have seen before, when you apply a resistance to the material, when you apply a pressure to the material, basically the aerogel decreases in size, the resistance is decreasing. Okay, that gives a change of slope, as we mentioned before. Good. I told you also the effect of temperature. When you apply a temperature gradient to the aerogel, there is a voltage developed due to the Seebeck effect of the electronic charge carriers. And then it appears as a shift in the IV curve. They are shifted like this. Very nice. Now let's have a look at the humidity. I told you also that at some humidity level, you have ions that kicks in, and they will be seen as a peak in the voltage versus time. And here, indeed, for those materials, we succeed to make this aerogel with this kind of feature, where you see that the peak is depending on the humidity. So the peak is basically here, the voltage, the Seebeck voltage at the peak is depending on the humidity. Then we have another parameter that we can read, basically, the humidity also. And we will decouple that versus time. So we will read the potential and we decouple that versus time. So as I told you before, this, when you do versus time, the peak value gives you the humidity, but the plateau value after a while gives you actually it is related to the electronic Seebeck voltage. So this, if you know the electronic Seebeck voltage, you can know the temperature gradient. So this is what we succeed to do, basically. And the amazing things is that those parameters are not cross-talking, they are not polluting each other. For instance, look at the Seebeck coefficient at different humidity level. When I apply a pressure, it's constant. Look at the resistance here versus humidity for different pressure, it's almost constant. So there is a window of pressure, humidity, and temperature gradient where actually we can read independently each of the parameter, and there is no cross-talking. So we completely disconnect the talking between those value by an intelligent design material. So one material that can read 3 parameters independently. So here, this is an example of the curve that you obtain then. What you get is then a set of IV curve. So this is the current, voltage, and time. And we just have collect a set of IV curve versus time. And we look how it looks like. You see the slope here. The slope is correspond then to the temperature, the pressure. The peak value here correspond to humidity, and the value at long time for the plateau correspond to the temperature gradient. So this is what you can read 3 parameters in the same time. Okay, I see how many minutes I have. I think maybe I can go just quickly through that. Or maybe
10 minutes.
Maybe I stop here. Sorry?
Another 8 minutes.
How many minutes do I have?
So you have 5 more minutes.
Okay, then I will show you a little bit the last feature. So now we are going to talk only about ions. So we are going to speak about electrolyte, polymeric electrolytes. And we are going to use one of their key features. I told you at the beginning, those ions have a huge Seebeck voltage. So the Seebeck coefficient of ions is 100 times larger than the Seebeck coefficient of electronic carriers, typically. So then it's very interesting to make a super sensitive temperature sensor or heat flow sensor. So you know thermopile, they are used for detection of heat flow, but they are typically electronic made of electronic materials. So here we take the challenge to make thermopile as a sensor based on ions and polymeric ions. So in order to have super high sensitivity. So the material that we are using is this material. It's a polymer. It's a copolymer actually, based on PVDF. It's a fluorinated polymer, which has a crystalline and an amorphous phase, basically. So these materials, they look like solid polymer, and when you can put ionic liquids into it. So it means that they can just swell the ionic liquid. So the ionic liquid is just a liquid that you put in, and this liquid is composed of cations, molecular cations, and molecular anions, and they really penetrate into this polymer matrix, to create like a gel. So it's very easy to create, to make, and it appears like a gel. Then we can look a little bit about the ionic conductivity, which is here in the blue curve, when we add more and more ionic liquid. So when we start to add ionic liquid here, the ionic conductivity increase. Just for the sake of comparison, you can look at the value of ionic conductivity for the pure ionic liquid, and you see that we are quite close to the value of pure ionic liquid, meaning that these polymeric gels are full of ionic liquid and are conducting the ions quite well. Now, we can look at the Seebeck coefficient of the ions, and we see a parameter which is here close to -4 millivolt per Kelvin. It is a very high value. If you just take the pure ionic liquid, you get much lower. You get less than -1 millivolt per Kelvin. So the fact that this ionic liquid is in the polymer matrix boosts this ionic Seebeck effect. In that case, since it's a negative value, these are mostly the TFSI anion that are thermodiffusing, while the cation are not very well transported by thermodiffusion. That's why you have majority the anions that are moving here. But what we make as a discovery is that when we start to add yet another material, which is a low molecular polyethylene glycol. So polyethylene glycol in low molecular can be liquid also. So you just add on top of this material the polyethylene glycol, which is liquid, in a liquid phase because it's very short polymer chain, and it completely penetrates in the material. And what is happening is very interesting, is that the properties, the thermoelectric properties are completely changing. So if you follow here, first, this curve here in red is the Seebeck coefficient of the ions. I told you at the beginning, before we add this polyethylene glycol, we get something like -5. I told you these are the anions that are mostly moving. But when you add this polyethylene glycol, you see that the Seebeck coefficient goes towards cross zero and goes to the other side up to +10 millivolt per Kelvin. So basically, by adding this polyethylene glycol, what you do is you promote now the transport of the cation that are becoming very well transported. So by controlling the composition of these gels, you can change the Seebeck coefficient from minus to plus, so which is quite interesting, because it's what you know, what you need to build thermoelectric modules. So thermoelectric modules like thermopile, they are composed of P and N junction, basically. So material with P with positive Seebeck coefficient, material with negative Seebeck coefficient that are put electrically in series, thermally in parallel. And what we did here, instead of a normal thermoelectric module or a thermopile with electronic carriers, is that we do that with these polymeric electrolyte with positive and negative Seebeck. And then here, for instance, with the 36 legs of positive and negative ionic Seebeck coefficient polymer, we get basically a very strong signal. So when you apply a small temperature gradient, you get a huge voltage, basically. So something like 0.3 volt per Kelvin. So it becomes a very sensitive material and device for reading temperature gradient. So now you can even amplify further the signal, because with this kind of large voltage you obtain for a few Kelvin, you can actually switch completely a transistor. So we make transistor based on electrolyte that are shifting at 1 volt or 2. And when you couple this sensor thermopile to a transistor, you completely can switch from off to on the transistor just by the temperature gradient, the thermovoltage, basically. And this is giving like a smart pixel for sensor using this kind of concept for very accurate temperature sensor reading. So just to finish as a conclusion, we have been using then the electronic Seebeck coefficient in conducting polymer to make aerial gel to create basically sensors that are temperature and pressure. When we look at humidity and we use the ionic charge carriers, we can also, in addition, have the reading of humidity. And then we use the ionic Seebeck coefficient, which is 100 times the electronic Seebeck coefficient, to get super high thermopile for the first time based. So thank you for your attention.
Thank you, Dr. Seebeck, for a nice, interesting talk on thermoelectric based sensors. We have got a couple of questions from the participants. What is the lifetime of ionic liquid based sensors?
The lifetime, you mean?
Yeah, like.
You mean the stability? But they are very stable. These are very stable material.
They are asking about self-life.
Sorry, I could not hear. Can you repeat?
What is the lifetime of ionic liquid based sensors?
Well, I have no idea about the lifetime, but they are used in batteries, and the batteries, they should have a lifetime of many years. So they are very stable material.
Another question is, can we use thermoelectric polymers for in vivo sensing and monitoring of bioanalytes? Can we use it for biomedical application?
For
biomedical applications.
For biomedical application, I mean, this is an area interesting, certainly. I mean, what we are doing, for instance, with these smart pixel or sensor is that you can create bandage that are reading the temperature in a very accurate fashion. So if you have, for instance, scars on your skin, and you have such a bandage with the electronic sensor and an array, you can read basically the healing. You can follow the healing of the scars versus times, because typically during those procedures you have a temperature gradient. If you have an inflammation, you will see suddenly a large temperature gradient, and then you can also detect infections, etc. So there are many possibilities, yes.
One last question. Whether is it possible to develop hybrid sensor using these thermoelectric and piezoelectric materials? So can we combine thermoelectric
because I don't hear very well the sound.
Can we combine thermoelectric and piezoelectric materials to develop a hybrid sensor?
Yes, indeed, this is something that we have done also. I have not presented that in this talk, but yes, we have been combining piezoelectric and pyroelectric together with these ionic thermoelectric sensor. So this is an interesting. This is quite interesting. For instance, the pyroelectric sensor they are very sensitive, and but they provide a signal that is not constant versus time. So, for instance, if you have like this burger alarm, if you put your hand, there will be a peak in voltage, but after the signal will decrease versus time, so that you lose somehow the reading of the temperature. You detect, but you cannot read the temperature. But when you combine that with this ionic thermoelectric material, you can have a much more stable and sensitive signal also. We have been publishing that also in some work.
Thank you, Dr. So thank you, Dr. Xavier, for a nice session, and thanks once again for accepting our invitation.
Yeah, it was a pleasure. Thank you. Thank you, everybody. Have a great day.
Yeah,
Thank
yeah,
you.
have
Bye-bye.
a great day too. Thank you.